Thank you, Professor Xiao, and also thank you, Professor Xiao and Professor Dai and Professor Xiangming here to give a talk this one. So as the Professor just mentioned, I have a very strong connection with Hong Kong. I did my PhD on USC and did my postdoc USC and also PolyU, and so it's glad to come back. And yesterday I landed in the morning. I feel it's a very nice environment, very sunny, bright, and warm. And also I have to take out a few layers when I land in Hong Kong. And at the moment in the UK, where temperature is high compared with the average, so there's a global warming effect. Actually, temperature being higher and higher year by year. It's just very wet, and Hong Kong is wet, but UK is even wetter, and also that and because of this further loss, so getting dark earlier. So here very bright city. So nice to be here again. So today I'm going to present some work about this carbonation. Okay, so part of this calcium carbonate saving for improving property of limestone calcium clay through in-situ aqueous carbonation. So for my talk, I'm going to talk about a little bit about the carbon capture, utilization, and storage, and how to reduce the cementitious materials country industry, and talk about various carbonation technique, and also factors affecting acceleration carbonation technology, which is where we focus on. And finally, talk about in-situ aqueous carbonation, LC3. That's finally making some conclusions. Okay, so this is actually one of the figures taken from this paper, and one of the co-author did, and one was the exchange program with me in my group, funded by CSC. Okay, so we talk about there's many things in carbon neutrality. Now, even nowadays, there's a kind of weighting down, trying to achieve the carbon neutrality by 2050, mainly by the little bit weighting down from the United States, but in Europe, they're still putting the top agenda for achieve carbon neutrality by 2050. So this is taken from the paper and published by Professor Xiao and also by the CSP and Zhongyin Li. They're top paper. But this figure is not from the paper. This paper only 3 pages. It doesn't have a figure, but this comes from it's called WeChart or Weibo. So basically, this way how to achieve the net zero concrete. We talk about concrete. There's different ways to achieve how they estimate which measures it can reduce the carbon. Okay, for 100% base point. Now 2020, we took from 2020 base point to 0, 2050. Okay. Again, of course, some of this is just for estimation. Okay, so we will kind of focus on a little bit on the use greener cement materials and also the way to reduce carbon and through carbonation. Okay, so the different ways of the carbon capture and there are huge projects. Every project could be multi-billion pounds. Okay, and it's just extract carbon from atom field and sealed it and consolidate on the deep ground is mainly is a waste mining site. Okay, like in the UK, in Wales, and they have used the coal mining. I think until the earlier or 30s of the 20th century, 100 years ago, UK still export coal to the world. But now all the coal mining has finished, and the deep coal mining site is 800 meters deep down the ground, and it needs to be filled. Okay? And so what people doing that, there's part of research project, large project in the UK, they're doing this one, and underground. And that's a university, Cardiff University are leading the research in these areas. Okay? And in other ways, carbon can use a valuable kind of resource. Okay? We can use carbon, coal-designed carbon, to making new sustainable products. Okay, so think about every year, humans and activities can emission around 38 billion tons of carbon in the atmosphere. That's huge kind of resource. Obviously, we have to be managing this resource because it can be very expensive to convert it as this material. Actually, so far, I'm telling you later on, and these are the network, so the carbon capture utilization project, and funded by European Commission. Okay, network. somehow actually research innovation project somehow you're trying to push to commercial. Okay? So if you check this one, city US airport, you will find the project. Okay? And these are the extracted from the website, how they making the carbon. So the target is not capture carbon from atomic field, because that concentration is too low. It's impossible. They're gonna capture carbon from the fuel side, fossil fuel or biomass fuel power station. Okay? And these usually have a carbon constraint around 20% or 15 to 25%. This possibly can can be captured. Okay, and the way to capture it, you can use either storage like a liquid gas, liquid LPG, liquid petroleum gas. Okay, and you can ship to other side. Okay, or you can extract it to the underground. And that's the way to do it. But if you look at this one, okay, so you need extract the carbon and go deep down the 800 meters deep underground. Then you will seal it. Okay, with a possible kind of cement is kind of a solution. Otherwise, it will be released again as an affair. Okay, so it's a very challenging. So you have hydrodynamical reactions. So now there's quite a kind of research trying to see how we can seal this carbon and this one. And this one paper, I think, is quite helpful getting this idea about this carbon dioxide and extraction and see on the underground mining site. But okay, the capacity so far we've had around the world, which you can do carbon capture and storage, it can only capture 38 million tons of carbon dioxide. Okay, but human society or hydrogenic carbon emission is around 38 million tons. Okay, 38 million tons. So in other words, we can only capture and storage 1,000th of carbon emitted by human society every year. Okay, this means actually carbon capture and storage actually cannot be actually a solution unless there's a huge breakthrough in technology. Okay, at the moment, okay, could you rely on the subsidies from other industries? So this carbon tax, carbon credit. Okay, so this is always important, but naturally, there's natural combination. Okay, if you look at kind of this steel manufacturing and the plant, a huge amount of this waste and hiding outside the plant, some open space and huge mining waste. Okay, and they will change the color. Okay, and this actually is a natural combination of under this atomic field carbon dioxide. Okay, so but it's very slow. The key thing is that the concentration of carbon dioxide is too low. In atmosphere, it's only 0.03%. 0.03%. I mentioned in the fuel side energy, fossil fuel energy plant, okay, the outfix gas is around 100% carbon dioxide. Okay, but this inspired people, inspired engineer. Okay, what can do controlled accelerated combination. Okay, and this is one of the earlier people talk about steel slag combination. It's molecular something. So this ideas combination, this one. So I know it's quite a lot of research project have been funded in the UK and not in China and in Hong Kong regarding the carbonation. Okay, so using in accelerated combination technology, you study higher concentration of carbon dioxide. This carbon dioxide will react with hydrogen products of cement like CSH, okay, or calcium hydroxide, and then they generate calcium carbonate. Okay, carbonate. This is solidly bonded the carbon. Okay, because if you're going to break down carbon calcium carbonate into carbon dioxide, you're going to need 1,400 degrees Celsius temperature, which is not possible. They can actually work and react with free calcium and free magnesium. Okay, the free magnesium and can be a problem for many materials because it can be expansion. Okay, so that's what we are using this technology, developing technology. Okay, so basically, if you talk about carbonation of cement materials, okay, basically is that reaction between cement itself, some component, C2S, C3S, and calcium oxide, and hydration product, CSH, with carbon. Okay, generate carbon, calcium carbonate, okay, also small amount of magnesium, so magnesium carbonate. Okay, slightly different magnesium carbonate, magnesium hydroxide is a different phase, slightly more complicated than calcium. And we have, I just got a PhD thing on magnesium oxide. Okay, so 3 ways that either do carbon mixing when they're mixing the injected carbon, or carbon curing. That's one of the main thing we're doing, carbon curing. And also you could recarbonate the aggregate, mainly recycled aggregate, okay? Then mix with the other component for making concrete without any difference from the current technology. So this is 3 ways to do that. Okay? So if you talk about curing, that's what I'm saying, curing. So carbon curing is happened in the first few hours after cement mixed with water, okay, and before final setting. Okay, so this process involves that the diffusion, dissolution, and ionization carbon dioxide into a pore solution of the cement paste. Okay, some pore solution. Yeah, because carbon dioxide immediately carbon and dissolve in the solution. Then, and there's also calcium ion leach from the cement clinker. Then they can react together to generate calcium carbonate. Then precipitation. Okay, the precipitation that could have a side effect. It could prevent further carbonation of other products because they cover uncarbonated cement particles, CSH. And we need a solvent. That's on later on we use some additive to prevent or trying to improve that dispersion of the generated calcium carbonate so that it will not cover the other part which are unhydrated. Okay? We have the problem, that carbonation could be a surface layer be carbonated, then it becomes very dense, where to prevent the diffusion of carbon dioxide into getting deeper in the body of the concrete block, so that and prevent the further carbonation. We use a so-called carbonation rate to quantify that effect. Okay. Other things talk about the carbon mixing. And generally, you're going to mix in the carbon dioxide with some particles, okay, and water. So basically, in the slurry stage, you start to inject carbon dioxide. So define carbon dioxide into that mixing process. Okay, and this has some advantage. Okay, but the disadvantage is that you have the well-controlled environment and it's not so efficient. Okay, so this is one. Now, so we just want to summarize what are the current carbonation technique. Okay, so one is dry carbonation. This one taken from one paper from Zhejiang University Technology. So, Ian was my visiting PhD student on the CC, and they developed this set of this they call CaCO, something from chamber. Okay, the co-development with tire manufacturers. So this is a typical dry carbonation for the products. You need higher certain areas and more porous particles, and you need to control the gas and the flow rate, dry carbonation. The dry carbonation good thing is that it's actually easy to proceed. It's easier to proceed, but it needs special equipment because you need to control the temperature. Later on, we'll talk about water factor controlling that efficiency of carbonation. And semi-dry. So semi-dry because it's a evaporating fat. Okay, so the particles going down in semi-dry and with the kind of gas flow. So you make sure that the particles are evaporating so that all the surface get a chance to connect the moisture and carbon. Okay, this is called semi-dry. Okay. Then wet carbonation. Okay, so we'll talk about later on more on wet carbonation or pressure carbonation. This is probably pretty much and used very often in research. Okay, but later on we'll talk about whether it's possible in the industry, how to the feasibility to scale out whether we can do it. So generally, you have a carbon flow and with this solution of cement particles. So you will have a very high and water solid ratio with carbonation, much more than the water carbonate cement ratio needed. Okay? Then they have semi-wet. Semi-wet is that they call this particles, okay, and regularize water and in a very humidity. Then generally this time you can saturate this one, make this one. So first thing you can pumping this saturated this solutions making that drying and accelerate the reaction between the particles and the solution. Okay, and we have semi-wet. So semi-wet, this semi-wet, and this one is you have a ultrasonic atomizers. Okay, atomizer. So keep this moisture and some kind of critical moisture and the particles. Okay, and make sure that they get maximum and possible exposure to the moisture and carbon dioxide. Okay. And there's other way people are doing that. Okay. Okay. So dry ice carbonation. They're going to mix the dry ice and the blocks with cement particles with cement materials. Okay, the solid, then adding water, very friendly. So the thing is that the way is dry ice trying to use the current technology making concrete without changing equipment. Okay, that's the dry icing mixing. And there's other ways and how to improve carbonation, because at the moment the carbonation efficiency is around 15%, 25%, maximum 25%. Okay, so there are people doing that will use the bacteria to improve the carbonation. So one of the work done by this Xiangming from the Southeast University in this bacteria and carbonation. Okay, so as I mentioned, most promising way, I would say, in my opinion, which could have a scale up, is so-called accelerated carbonation and water and dry carbonate technology. So we done some. This is my research partner from University Bureau Interior from Portugal. Governments we have currently we have 2 European projects and working on this one. Currently one finished, one is ongoing, and this is his lab. So my student went to his lab with the settlement. So this one. So if the accelerated carbonation is affected by the carbon concentration and temperature, reacting temperature and pressure, you can see, and also moisture content. Okay, sometimes you need to well-designed moisture component, and I had a chance to Prof, and he actually mentioned we need to do some modeling use kind of to find out what's optimal moisture component and moisture concentration, and use a semi-wet carbonation. Okay, and particle size surface areas. Basically, you need this particle to get maximum chance to contain moisture and contact the carbon dioxide, so that you improve the carbonation. Okay, and also the concentration is case factors. Okay, in the research you use nearly 100% carbon concentration, but nowadays move towards like 20% and use that flue gas from this industrial plant like and cement plant like this also burn power station in flash and gas. Okay. And generally, higher carbon concentration, you've got a higher carbonation rate. And temperature as well. So usually we're seeing 50, 60 degrees fine. So you need normal temperature probably not strong enough to generate and the kinetics and needed for improve the carbonation. But if you have a excessively high temperature, you may lead to undesirable side reactions. Okay, and affect the stability of the carbonate. And pressure. Okay, pressure. That's why you need special equipment for this chamber for dry carbonation. Okay, generally you have a high pressure to improve the diffusion of carbon dioxide into the body of the concrete products. Okay, that's and high pressure. But obviously high pressure means a higher energy. You're going to generate more carbon emission. Moisture content is sometimes called as a subcritical and moisture component. Yeah, moisture component, and particularly in the semi-wet and semi-dry is carbonation. Then you have particle size in certain area, obviously. Okay, smaller particle size means higher spatial surface area is going to higher chance to contact carbon dioxide and moisture to improve the combination in reaction time. So you can shorten time is better. Okay, some people talk about that 24 hours. Some people talk about a few minutes. Usually just 1 or 2 hours. So we found that when we try to get in like a half an hour, this is why. Why with the half an hour? Later I'll talk about. Because and in the cement plant, okay, the whole process and was for instance 20 to 30 minutes probably for the gas extracted from the chimney to go downstream to the whole production line. So this is one of the companies in the UK. Actually, they also have branch in Europe. They call carbonate system. Okay. It's one of our partners for European project. Okay. They developed this accelerated carbonate technology used in the larger scale, and in one of this, they have several sites. Okay, this is one of the sites in it's a vehicle cement product, vehicle cement group, vehicle cement group. This is one of the largest cement group in Europe. Okay, and this is one of the plants in northern France. So carbon-8 technology, they are company that developed this whole system, which upscaled at this plant. They can generate around 12,000 tons of this aggregate, period. And it can capture 4,000 tons carbon dioxide. Okay? Imagine, think about that. It's 4,000 tons. Okay, as mentioned, over 38 billion tons carbon emission every year. Okay, but even so, this is actually very large. I wouldn't say very large. Sorry, it's a medium size kind of trial in Europe, which is carbonation. Okay, so their products. Okay, their products basically is kind of artificial aggregate. Okay, they use that the flue gas from the chimney of the cement production in vacuum cement production line, make this one. Okay, and they actually started with quite of the subsidies from the research project and from commissioning. But just recently, I heard they went to administration, which means the bankrupt. They don't have enough funding to sustain the technology. It's unfortunately. So this are the if you search the circle view, that's mainly the products. I know nowadays in China, many kind of innovation project doing this artificial aggregate, mainly similar to this. This is one of the artificial aggregate used for making the concrete in the future. Okay, and this is currently one of our project, our Europe project called biomimicry, inspired eco materials and the solution by co-utilizing waste and carbon dioxide. We use carbonate technology making various kind of waste material. You have silicon, you have calcium, you have magnesium. There's different kind of waste material. Or it can be carbonated. Okay, so our target is to design some products and co-design products utilizing carbon dioxide and its regular waste. And some of them use nature and mimic nature by mimic nature. So this is a project website. It's a project and 4-year project starting 2023 January and will finish end of next year. Now today I want to talk about one of my pieces in the down work uses aqueous in-situ carbonation. Okay, and why we choose limestone calcined cement. Okay, one of our students will also use other magnesium oxide cement. We also done this one. So this student focus on the LC3. So main thing is we deal with that the clinker, and then so put on cement, you have 95% by weight, clinker. Okay, these are main things which the production clinker generate quite a lot of carbon. So we're trying to use other ways to reduce amount of clinker. Remember in the beginning of the my presentation slide showing the journey to the zero carbon concrete. One way is to try to reduce the clinker. Okay, so we are thinking of reduce clinker to 50%. Clinker, we need clinker because it has to generate how very quick to generate earlier edge strength. And that's a beautiful concrete. So you need one day you can split the mold into the other layer, other stories, and that's concrete, can't replace concrete, and that's mainly one of the reasons. So if we can reduce from 95% back on cement with 95%, they have clinker. Now it's only 50%, okay, 100%. See, so we're going to replace this 45% with 30% calcium clay, 50% limestone. Okay, limestone. The reason is because calcium clay, you can find calcium clay everywhere across the globe. Okay, and same as limestone. While others, SCM, cementitious, supplemental cementing materials are getting less and less, especially in Europe, such as fly ash and UK, or we closed down all these coal burning power stations, so we wouldn't have a fly ash anymore. And steel slag, manufacturing of steel is winding down significantly in the UK. We only have 2 plants now in making steel. Okay, making sense. There's even have problem. One of these plants still have to require the government to subsidize it, otherwise they can close down. They close down. So we wouldn't have a steel, and the slag is now a GBS is similar price of Poland cement, okay, and so on. So that's why now many of focus of research move to LC3. Okay, and the reaction mechanism LC3 showing that one. Okay, so we found a small amount of calcium carbonate. They can react with the aluminum phase. Okay, from calcium clay. Okay, remember we have silicon phase and the aluminum phase. Okay, and the silicon phase and react earlier, they can hydrogen earlier, but aluminum sometimes sometimes calcium clay have a much higher aluminum phase than the Poland cement. So that's why we say whether we can use this and the carbonation technology to generate this holocarbonate aluminate, monocarbonate aluminate, which could have positive effect on the strength development. Okay, so the calcium carbonate or even ordinary calcium carbonate have 3 functions. One is act as nucleation sites, so that can have quite a base for CSH, general CSH, and CSH contribute to the strength. Okay? And also because the particles are very small, okay, you have fading effects. Okay? Again, it has some reaction. Remember, what's small amount, it can react with aluminum phase. Okay? So there's 3 basic effects. Okay? We are trying to generate even smaller calcium carbonate, we call nano scale calcium carbonate. Okay? They have ultra high strength in certain areas. Okay? They provide much more nuclear size. Okay? And because they're smaller, they have much better fading effects. But because they're smaller, the nano scale always have problem of agglomeration, which will jeopardize its performance. Okay? We're trying to improve its disposability, but so that it can maximize its contribution to unlock its potential. Okay, and also some people find it could hold the very minor scale potential stress concentration, which is not good stress concentration. But we are not dealing with the stress concentration this time. Okay? So if you do the mechanism is that again through this aqueous in-situ combination, release calcium, okay, and at the same time, the hydration generates carbonates and hydrogen products. They have carbonates from membrane. Okay. Then reaction with this calcium legacy of calcium carbonate, a reaction with one calcium carbonate generate nano scale calcium carbonate, and this nano scale carbonate further as a nuclear site. Okay, holds to hold this CSH and also feeding that macro cracks, macro pores. And improve the microstructure, further improve the durability and strength. Okay, so this is just a mechanism, mechanism. Okay, so we need to do the way we use that. As mentioned, we said we're trying to reduce that time that you need for the whole process to around half an hour. This is our target. Okay, we use carbon injection 10 minutes, 20 minutes, 30 minutes, 40 minutes. That's what we done in the lab, and we measure and pH. We measure that's the temperature and which is and the way to say the hydration. Okay, and finally we found that the temperature, highest temperature around 25 minutes at 45 degrees. While we started as as a room temperature around 20 degrees, and the final pH still can maintain 11.7. Okay, I know that normal concrete that's the pH around 13. It's not drop too significantly because you don't want to drop too significantly because it would get and prevent is good thing for concrete and will have a passive field which protect for the reinforcement from corrosion. Okay? And we also found in terms of particle size, okay, after this injection of carbon and aqueous carbonation, we found there's a bimodal distribution where small particle size and also big particle size. So there's two peaks rather than just one peak. Okay, if you're doing one peak, two peaks. Okay, the reason is that you have a smaller particle size, which is good. Then I'll talk about they're less than 30 nanometers. Okay, that's the non-detrimental particles. Okay, and then the later, this is bigger size. The reason is because of agglomeration. Okay, that's agglomeration. That's the so we don't want it, but it cannot be avoided. Okay, agglomeration. So we think that we do more particle size. So generally, it's that's and medium particle size. Okay, so we found that 20 minutes and 30 minutes and 40 minutes and similar kind of particle size. Okay, medium particle very small ones. Over 40 minutes is better, even smaller, but it could also consequence. Okay, okay, and the surface areas. Okay, this one 30 minutes. Okay, is those general particle size close to 20 minutes, but its surface area is much bigger than 20 minutes. Okay, it's close to the 40 minutes injection. Okay, so we think that for 30 minutes is good enough. That's what later research focus on 30 minutes injection. Okay. We also look at the microstructures for that clinker without carbon dioxide and with carbon dioxide. That's pressure injection. So you can see that the conform you have much smaller particles. Okay, you look at this 1 micron. So this is basically this will be less than 100 nanometers. Okay, that will prove that in a way it's a nano size and calcium carbonate. And our papers in question whether it can prove that one. We need other layers to further prove this generates calcium carbonate on nano scale. Okay. And we also do this DG geolysis, the way we kind of find out how much carbon is sequestrated. Okay, sequestrated. Okay. So we also try to find a morphology water. So calcium carbonate have 3 morphologies. So some are more stable, some less stable. Okay. So we find that main morphology is calcined, and that's we can uptake or sequestrate 14.6%. Okay, with 40 minutes injection, 40 minute injection. Okay, then inspiring this. Okay, inspiring this. Okay, we are now trying to integrate this in-situ combination with SC3. That's it. Before that, we do is a clinker. We use a clinker, mainly whole clinker. Okay, pure clinker. Now we say SC3 only have 50% by weight of clinker. Okay, we take half of this clinker, over 25% of cementitious materials. Okay, over the cement 50% are clinker. Compared with Portland cement, they are 95% clinker. With 50% of clinker, we take half. This is 25% overall. Okay, we accommodate this half of the clinkers in SC3, then mix with the remaining part, okay, and making this new integrated and SC3 integrated in-situ combination. Okay, we use this again. We do carbon duration, carbon injection, 10 minutes, 20, 30, 40 minutes, and injection rate 5 liters per minute. Okay, and we do this also to the hydrogen heat with the heat flow and also this accumulated heat. So you can see that we have 2-phase aluminum and silicon aluminum. Silicon heat feeds hydrogen earlier than aluminum. Okay, so compare with this one without the combination. So this is red line without combination. We can see that with combination, the silicon feeds hydrogen shift earlier. It start earlier. Okay, and aluminum phase hydration again shift earlier or shift left. So reaction of silicon phase and aluminum phase all accelerated. Okay, why we need to assert it? Because LC3 generally compared with the Portland cement, they have a lower earlier strength. That's the horns of LC3. Okay. So after approximately 18 hours, that's 18 hours, the total heat rate S3 containing carbonate cement and cement is still higher than acid and higher than that of QS without combination. Without combination. So this is the way is that if you can improve the strength up to 18 hours, which means that you can actually demold it for next level of construction. Okay, but we found that because of the injection, we found that no passive fluidity. Okay, basically the workability is reduced. Okay, become more sticky. That's why we need some kind of superplasticity later on, and sitting time is shorter because the hydration move earlier forward. Okay, both the sitting phase and remain phase, and sometimes it's a flash setting, which could be a problem. Okay, and we found the 30 minutes injection and the compression strength increased by around 25 to 42% at different ages. And you see that in earliest age strength increase, and even the standard 28 days is still increase of more than 40%. Okay, but in 40 minutes and injection, you have a slightly lower compression strength. Okay, remember earlier stage was saying in 40 minutes injection, you have a general particle size, medium size smaller, which is good, and also that surface area bigger is good. But actually, it doesn't mean that the higher strength bit and higher. So this is why that's why we abandoned 40 minutes. We further look at the QXRD, try and find out the phase generated through this in-situ combination with without and carbon dioxide. Okay, so we see that roughly have same all the different phase, only that the proportion are different. Okay, and one day the proportion of calcium carbonate changed significantly. Okay, because of earlier and stable hydration occurring combination. At 28 days, because now we have in-situ calcium carbonate, promotes the formation of more amorphous capsule, okay, capsule, and also by limit the formation and H3MC action. Later on, we'll see the H3MC that could be because they have less H3MC generated. Okay, it doesn't have the effect to improve the addition of weight impact. Okay, this is the downside of this technology. Okay, and we look at that and HCMC generated and in this case pure XRD. Okay, at 3 days and roughly you see even 30 minutes showing that the highest amount of HCMC. Okay, that's because the nano calcium carbonate reacts with the HCMC. This one. Okay, so optimal calcium carbonate CH calcium hydroxide and the nano calcium carbonate content in the this is in the 20 minutes and 30-40 minutes roughly is as 20 minutes better. Okay, but 28 days and showing some different scenario. Okay, and nano calcium carbonate really reacts with calcium hydroxide to form HCMC. Okay, that's why the strength given and is not as good as we expect. Okay, and but the seeding effect is more pronounced for property enhancement. Okay, so in other words, we see that this nano calcium carbonate has 3 functions, right? One is seeding, nucleation, one is filling, okay, and the third one is carbonation. Reaction, still we're in aluminum phase. So the research shows that the nucleation side is more pronounced and for this technology. Okay, and we also know the pore structures in low field NMR in the pore structures. Okay, but generally, I think that we need to have the pore was less detrimental. Usually, if the pore size is less than 50 nanometers, is less detrimental, much less detrimental. Okay, so in-situ combination needs to increase in the proportion of pores with less than 50 nanometers. Okay, this pore has no kind of detrimental effect to the property, strength, durability for concrete. Okay, with 40 minutes injection, okay, and we have excessive combination, increase the pores and smaller pores, which looks like good. Okay, but decrease the combination strength. Okay, and we found this one. So we found that we need optimal combination duration. In this case, we think 30 minutes is better. Okay, and we also want to adjust the morphology of the different calcium carbonate generated. Okay, we have 4 morphologies. Okay, so we have done some research using the amino acid to regulate hydration carbonate of magnesium-based cement. We not just use one, whether it can use for LC3. So we use different kind of aluminum and amino acid, 4 types of amino acids. Okay, and we have this. We want this more of this one better right. Okay, so in terms of stability, this is more stable, and this is less stable, but less stable could be better for carbonation. Okay, for carbonation. For this generator, this properties. Okay, so we also need to deal with this problem with workability, okay, workability issues, and especially if we want to this kind of like 3D printing, we will have to have to consider this one. Okay, and particularly if you have the upscale this technology, obviously you're doing small scale in the lab, that's not big issue, but in upscale, you need to consider that's the workability. So we look at these 2 types of glutamic and glycine acid, and we look at this one and how the fact is the better right that we use duration 10, 20, 30 minutes, and we reduce the carbon flow. Okay, so you can see the difference from the amorphous calcium carbonate better right. Again, you can see that all the phase appear and all the different kind of formulation with different amino acids and on the different injection site. Only proportion are different. Some proportion are better, and indeed some are better in certain stage. It doesn't mean better always better. Okay. So the combination products primarily are water-white and amorphous calcium carbonate, okay, with this the amino acid moderation. Okay. And crystallinity of water-white increase with the combination time, generally increase with combination time. Okay. So if you look at the water-white, this one, so these have some consequence of the final properties. Okay. So as I said, we use around 10% of this. Half of the printers for this one. So this is what we call based on optimal combination time, 30 minutes. We found. Okay, look at that's the strength event. Look at the surface specific areas. Look at that's the particle size. Okay, and use these 2 different amino acids. Okay, the 2 tests, and they found that this during aqueous combination, okay, the general is carbonated SE3 with glumatic and carbonated S3 with glucoside. Okay, the compare with that carbonated S3. This one we do this one comparison. Okay, and we found that initially and the setting time, you can see the setting time. Okay, and also final setting time. Okay, so roughly you see that initial setting time and is around 200 to 400 minutes. Okay. The final setting time could do up to 550 minutes. Okay, so the fluidity of the carbonate containing glumatic acid and glycine acid increased by around 60 to 30%. Okay, that's the fluidity, which is better. Okay, which well. Setting time of the carbonated SE3 containing these 2 amino acids increased much more. Okay. Remember, earlier we said injecting carbon dioxide into the clinkers in SE3, it could cause faster setting. So with this amino acid, we can delay the setting and give the operation and time for further operations. Again, in terms of the strength, okay, we use that volume ratio. Robinson S3 without carbon injection, S3 S3 without carbonation, but with glumatic. Okay, carbonated S3 with glumatic, and S3 without carbonation, without carbon injection, but with glucine amino acid. Carbonated and S3 with glucine acid. So we do this comparison test. Okay, we found no early combination strengths. Okay, with all amino acids. So amino acids actually bring the low and early age strengths. Okay, this is decreased combination strength S3 and combination S3 with glumatic and also S3 with glucine by 50 to 18%. Okay. Originally, we think about it that improve as well. But greater strength at later stage. Okay, so earlier stage, the strength reduced back, and at later stage, 28 days, even longer, you go improve the strength. Okay. And these are proved by this hydration test result. Okay, so you can see as with this and glumatic and glucine and amino acids. Okay, and the peak are reduced. So dash one lower than the solid one, and the dash one lower than the solid one. That's why you see the early strength is lower. But the cumulated hydration peak, which is actually is a indication of the overall hydration effect, is similar without is not much different, particularly with this L3. Okay, no. See, so you have some different, but this one not much different. So the conclusion is that earlier reaction of the aluminum phase. Okay, remember what silicon phase, the aluminum phase with L3 with the carbon injection was observed. Okay, and this is consistent with previous results. And except the L3 with the glucine, the other samples, okay, the reaction with silicon and aluminum phase were suppressed. They'll reduce the one. Okay, after combination, the total gain release of the simple containing amino acid is decreased. Okay, it's decreased. Okay, and we look at that again. Look at that different kind of component of this different phase generated. Okay, we see that water right in order to promote the formation HCMC in early stage, and decrease amorphous phase content of formation HCMC at later stage. Okay, the earlier stage has less, but this increase in the later stage. Okay, that could be good for durability, and no water right and has been generated and after this one. Okay. And the DTG result kind of quantify how much and carbon dioxide will be also sequestrated. Okay, we are doing this 3 days and 28 days. Okay, and so the 28 days you have with glucine carbonated carbon dioxide carbonated Lc3 as more AFM than this without glucine or then glumatic. Okay, and AFT in this carbonated Lc3 with glumatic shows relatively higher greater growth rate. Okay, so show this one. Okay, and further quantify with 28 and 90 days. Okay, we have find that and similar conclusion. So the content anti-9 day increase with glumatic amino acid. Okay. Okay. We also further look at the pore structures. It was mentioned that we want much more non-determinate pores, which is particle size less than 50 nanometers. Okay, so we look at the medium particle size and critical particle size with different formulations. Okay, and we found that and have this 28 days, 90 days. Okay, and some of this volume, and also the main thing is from 28 days, 90 days. Okay, from combinated Lc3 with glumatic and combinated Lc3 glucine, the medium pore size increase 20% or 8%. Okay, compared to one, and the porosity also decrease. Okay. And pore volume fractions with different pores. So these two pores, okay, and together these are less detrimental. Okay, so for grammatical and into this carbonated acid3, and this is 10 to 15 nanometers pore and decrease 10 meters pore, less centimeter increase. Okay, with glucine, okay, and its pore size bigger than 100 nanometers decrease, but less than 10 nanometers increase. This can actually explain why the behavior of the material. So if I may draw some conclusions, so basically we talk about the combination of cylinders and solid waste. Okay, we're making concrete in waste, and it could be a feasible solution to accelerate our journey to carbonation. I say accelerate, okay, and generate. But there are various carbonate technology development and dry carbonation, wet carbonation, semi-dry, wet, and even different kind of additives such as these bacteria. Okay, or these all have been developed, but I have to say that most of them have not been tested at a larger scale. So far on lab scale, very small scale. Okay, and my research is talk about aqueous combination, later in-situ formation of calcium carbonate, which is nanoscale, approved nanoscale. Okay, and which is interspread with geophase and adhere to the surface of certain particles. It's needing to increase specific surface areas, okay, and which provide additional nuclear insight. Okay, this accelerates hydration kinetics of the both silicon phase and aluminum phase. Okay, and the progression and the progress consumption of polymer dye CH, okay, during the precarbonation restrict metal formation HCMC. Okay, so this is a trade-off because HCMC equal less HCMC and less early edge, lower early edge strength. We found this in situation generated a native calcium carbonate significantly improve component strength of Ac3. Okay, this is what initially we want. We want to improve early strength of Ac3. Okay, and we found 30 minutes injection is good enough. We're down to 30 minutes, 10 minutes, 10 minutes, 30 minutes, 20 minutes, 40 minutes. And with 30 minutes injection, carbon dioxide uptake can improve around 50%. And the reason is that this refine the pore structure. Okay, reduce the pore structure, many countries pore size is between 10 to 15 nanometers. They are less detrimental to the strength. Okay, and the proportion of fine capital pores increase as well. Okay, so this markedly improve that early edge strength and up to 100 days. Okay, and also long-term strength development. We also use amino acids. We have looked at 2 amino acids, chromatic and glucine. Okay, kind of say effect on this and different kind of phase with calcium carbonate phase. Okay. We found that wet wire with relatively well-defined crystallinity can be prepared within 30 minutes. So 30 minutes, that's why we right. But the earlier age complexation with the calcium ions and seriously handles hydration silicon phase. Okay, so this one they prolong the setting time. This one reduce at earlier strength. Okay, so this is the trade-off. We use the amino acid. Okay. But we do find that amino acids in other types one is good for magnesium oxide carbonate hydration, which we published one paper last year. It's done by other people. Okay. So I think this is last slide. Thank you.